Hi friends, I'm Sachin Malhotra. I'm going to be solving homework number 6 for EL6303. The question 1. The joint density function of x and y is given as 1 plus xy upon a, where modulus of x is less than y and for modulus of y less than 1 and 0 otherwise. So first we have to find a so that the joint density is a valid density. So we know that the area under the joint density equals 1. So just putting those values as fxy of x and y dx dy equals to 1 and integrating it from x equals to minus 1 to 1 and y equals to minus 1 to 1. So this is a trivial integration where 1 plus xy dx dy, first integrating it with respect to x and then with respect to y, we get a as 4. For the second part, I have been asked to calculate our x and y uncorrelated. So we know that the correlatedness is given by expectation of xy minus expectation of x into expectation of y. So for uncorrelatedness, cxy should be 0. So we can say that expectation of xy minus expectation of x into expectation of y is 0, or expectation of xy equals to expectation of x into expectation of y. So let's first find out expectation of xy. So 1 by 4, that is a, xy into 1 plus xy dx dy, and integrating it with respect to the same limits as x equals to minus 1 to 1 and y equals to minus 1 to 1. So integrating this out, we get expectation of xy equals to 1 upon 9. Similarly, finding out for expectation of x, where we multiply x with fxy dx dy. So integrating this again, expectation of x becomes 0. So we can clearly see that when expectation of x is 0, so expectation of xy cannot be equal to expectation of x into expectation of y, since this is a non-zero term and anything multiplied by 0 will become 0. For the C part, we have to find are they independent. So we can clearly see from the above part that expectation of xy is not equal to expectation of x into expectation of y. So it implies x and y are not independent. For the D part, I have to find the joint density of x square and y square. So let's assume that z equal to x square and w equals to y square. So solution of x and y are x equals to under root plus minus z and y equals to plus minus root w. So these are 4 roots. Now let's find out the Jacobian in terms of x and y. We know that Jacobian is given by the determinant of dz by dx, dz by dy, dw by dx and dw by dy. So this comes out to be 2x, 0, 0 and 2y. So this comes out to be 4xy, where x and y can be taken from the 4 values that we found, that is plus minus z and plus minus w. Now let's find the probability density of in terms of z and w. So this is given by 1 upon z xi yi into fxy of xi yi, where xi yi are the roots of the z of x and y, that is plus minus z and plus minus w. So putting in the values, and this comes out to be 1 upon 4 root z root w fxy root z into root w, fxy of root z root w. So this terms comes out from our Jacobian, that is 4xy, x is root z and root w. Similarly for root z and minus root w, similarly for minus root z and plus root w, and minus root z and minus root w, and just putting in the fxy in the similar terms. So this becomes 1 upon 4 root z root w into 1 by 4 taken out as common, and fxy is 1 upon 4 1 plus xy. So x is root z and root w and so on. So this becomes 1 plus root z root w plus 1 plus minus root z minus root w into root w, and 1 plus minus root z root w. So these all terms cancel out and we are left with 1 upon 4 into 4 into 1 upon 4 root z root w. So our fzw becomes 1 upon 2 root z into 1 upon 2 root w for z lying between 0 and 1 and w lying between 0 and 1. Now the fifth part asks us to calculate, prove x square and y square are independent. So let's find out the fz of z. So we know that z lies between 0 and 1. So this can be calculated out from the density of z and w into dw, integrating with respect to dw. So 1 upon 2 root z to 2 root w into dw gives us fz comes out to be 1 upon 2 root z. Similarly, we can find for f of w, and this again comes out to be 1 upon 2 root w. Thus, we can clearly state that f of zw is equal to f of z into f of w. So hence they are independent. Thank you.